Let's look at 6.4 and 6.5. This is about the central limit theorem. So I went ahead and wrote the definition on here for you. So the central limit theorem is, I'll let you write it down. How about that? I'll let y'all pause it. So there was a little mistake. I said by a normal distribution twice. Thanks for pointing that out. So for all samples of the same size n, where n is greater than 30, so that means your sample size is greater than 30, the sampling distribution of the sample mean x bar can be approximated by a normal distribution with mean of mu and a standard deviation of that, with the square root of n on the denominator. So practical rules. If the original population itself is not normally distributed, so let's say the original population is uniform, skewed, or otherwise, and you have samples greater than 30, the distribution of the sample mean can be approximated reasonably well by normal distribution. The approximation gets better as the sample size of n increases. If the original population is itself normally distributed, then the sample means will be normally distributed for any sample size, not just where n is greater than 30. If the original population is not itself normally distribution and n is less than or equal to 30, then the distribution of the sample mean cannot be approximated by a normal distribution, and you cannot use the central limit theorem. So you must have either it's already a normal distribution or it's a different kind of distribution, but the sample size is greater than 30. Then you can use a normal distribution to approximate it. So here are the formulas: the mean of all values, x bar, standard deviation of all values of x bar, and then the z-score. So this one is new. We were able to find the z-score similar to this, but the thing that changed is instead of using, I believe that's theta, then we're using theta over n's square root of n. Let me double check that symbol. Theta symbol. Okay, I think it is theta. Okay, so when should I use the central limit theorem? So we need to ask ourselves a question. Does the original population have a normal distribution or the sample size is greater than 30? So if this is a yes, then you can use the central limit theorem. I'm going to abbreviate CLT. So it's saying if the original population is a normal distribution or n is greater than 30. If not, then do not use. So that is something you have to check before you can use the central limit theorem. All right, let's go to the next page. Are you using a normal distribution with a single value of x or a mean of x bar from a sample values? So if it's an individual value from a normally distributed population, use what we learned in section 3, 6.3, and find the z-score. So remember this formula, x minus x bar over theta. And that's how we find our z-score. That's how many standard deviations we are away from our mean. But if it is not a normal distribution, but it has a sample size that's greater than 30, the central limit theorem uses this formula. to find the z-score. Okay, there are two different distributions. So the distribution of the original population may be normal. Or it could be uniform, it could be skewed, but it may be normal. But the distribution of the sample means will be normal when our sample size is greater than 30. Theta x bar is often called the standard error of mean, and we can abbreviate it with SEM. And it's actually called sigma. I was saying that wrong. So this is the sigma. X minus mu over sigma over the square root of n. Okay, so our first example, they've given us a situation in a graph. It says computers are often used to randomly generate digits of telephone numbers to be called for polling purposes. The digits 0 through 9 are generated in such a way that they are equally likely. The first graph shows a histogram of the 500,000 generated digits, which appear to be a uniform distribution. So this histogram of the 500,000 generated digits, this is our original population. When we have 500,000 digits and they're grouped into 5,000 samples, with each sample having 100 values, that's our sample size, the mean for each sample means are shown in the graph. So we have a uniform distribution, and that uniform distribution tells us that each number is equally likely. So this is our original population distribution. And it's a uniform distribution. And then we would use the central limit theorem. See how this looks now? Looks like a normal distribution. So even though the original 500,000 digits have a uniform distribution, the distribution of the 5,000 sample means is approximately a normal distribution. So this is the 5,000 sample means when our n value is 100. So there are 100 digits in each sample, and there's 5,000 samples. So this, you would use the central limit theorem so that we would have a normal distribution. Okay, let's look at example 2. When designing elevators, an obviously important consideration is the weight capacity. Did y'all ever look at the weight capacity? There's usually a plaque or something that tells you how many people can be on there or how much weight can be on there. So this, we would need to use statistics in order to determine what is the best weight limit and also how many people. So it says an Ohio college student died when he tried to escape from a dorm elevator that was overloaded with 24 passengers. The elevator was rated for a capacity of 16 passengers with a total weight of 2,500 pounds. Weights of adults are changing over time, and the following table shows the values of recent parameters. For the following, we assume a worst-case scenario in which all the passengers are male, which could easily happen in a dorm setting whenever you have a male dorm and a female dorm. If an elevator is loaded to a capacity of 2,500 pounds with 16 males, the mean weight of passengers is 156.25 pounds. So think about that. It says 16 people can get on that elevator. What if they're all males? Think about this. Do you think that every one of them is going to be this or less? If you really stop and think about it, you might have some overweight guys. You might have some that are just really muscular and they're over the 156, because 156 is kind of small for a male. So this does tell us that our mean weight for males is 182.9. Standard deviation is 40.8. And it's already a normal distribution. So what we are going to do is we are going to use the normal distribution, and we are going to find the probability that one of them has a weight greater than 156.25. So we're saying probability that X has a weight that is greater than 156.25. So let's find our z-score. We're going to use x bar minus mu over sigma. So this would be 156.25 minus the 182.9 over 40.8. So go ahead and put that in your calculator. Okay, so it's negative 0.65. And we are asked for, whenever you do your normal distribution, you know that your mean is 182.9. Well, this number would have to be less, so this is 156.25. It's saying find the probability, so that's the area to the right. But whenever we find the area using our table, we always find the area to the left. So we're going to have to find the opposite. We're going to have to do 1 minus. So this is the negative z-scores. We're going to find the area to the left and then subtract from 1. So negative 0.65, 0.2578 would be the area. So right here, 0.2578 is that area using this z-score. So we would have to do 1 minus that to find the area to the right. .7422. So this equals 0.7422. So that seems like a pretty good probability, right? Find the probability that one randomly selected adult has a weight greater than. So is that a good thing or a bad thing for this elevator situation? Yeah, that's bad. That means more than half of randomly selected, males are going to weigh more than this, which is not good in this situation. They're going to overload that elevator. So this is just using our what we've already learned from 6.3. Or did we learn this from 6.3? I feel like we learned it from. Yeah, it was last week. Maybe 6.2. So now we are going to find the probability that a sample of 16 randomly selected adults has a mean weight greater than 156.25. So instead of just picking one adult and finding the probability of that, we're finding the probability of a sample of 16 having a mean weight of greater than this probability. So we're doing the probability that X bar is greater than 156.25. And so on this one, I used X because we were just looking at one value. This one, I'm using X bar because we're looking at the mean of 16. From this, I also know that N is 16. So I'm going to use the z-score, and then I'm going to find the area. So the z-score, because we're doing of the mean, we're going to add the divided by the square root of N to it. So 156.25 minus the 182.9 over 40.8 over square root of 16. And this is going to give us our z-score, which we'll have to find the area. But again, whenever we find the area, we're finding the area to the left whenever we do our table. So we are going to have to do the 1 minus. Okay, so whenever we do this, it's very similar to what I had. So I can go back up here and just change it, divided by square root of 16. So negative 2.61 is my z-score. So that's what this is. So I can use the table to do my area to find this. So it's again a negative z-score, so negative 2.61. So negative 2.61, 0.0045. So this area right here is 0.0045. So to find the area to the right, I would subtract that from 1. .9955. So the probability that you take a sample of 16 randomly selected adult males and find their mean weight, and it will be greater than 156.2, is basically 99.5% probability. That's not a good sign. I think the elevator needs to be re-rated based on these numbers right here. Okay, let's go to example 3. Men are typically heavier than women and children. So when loading a water taxi, let's assume the worst case scenario in which all passengers are men. Based on the data from the National Health and Nutrition Examination Survey, assume that weights of men are normally distributed with a mean of 172 and a standard deviation of 29. So let's go ahead and write that. Standard deviation. Find the probability that if an individual man is randomly selected, his weight will be greater than 175. So probability that some man's weight is greater than 175. So again with this, okay, so we have 172 as our mean. And then our standard deviation is 29. And then we're wanting to know 175, greater than 175. So we're wanting to know this area. Is this going to be more or less than 0.5? The area 172 to infinity. It's going to be more than 0.5 because it's past our mean. So what we're going to have to do is find this area and then subtract it from 1. So let's do probability that x is greater than 175. So we need to find our z-score. So we're going to subtract what we're looking at, the 175, from our mean, divided by our standard deviation. Math decimal. Our z-scores are about that. So then we want to find the area of 0.1. So this will be on the right side. So 0.1, 0.5398. So this area right here is 0.5398. So then to find the probability of greater than that, we do 1 minus 0.5398. .4602. So less than half, about 46% of men will be greater than 175. Part B, find the probability that 20 randomly selected men, so our n equals 20, will have a mean that is greater than 175. So probability that x bar is greater than 175, so that their total weight exceeds the safe capacity of 3,500 pounds. Okay, so whenever we do our z here, we are going to do the sigma divided by square root of n. So we'll do the same thing, 175 minus 172 over 29 over square root of 20. And since this is already a normal distribution, having 20 in our sample size is okay. If this was not a normal distribution, then we couldn't do the approximation to normal. Divided by square root 2. Oh, 20. Thanks. There we go. Okay, so our z-score is 0.4626 or 0.47 is what we'd want to use because of rounding. So we would go over here, 47. Oh no, it'd be 46. Why am I saying that? Y'all should have corrected me. We would not round that up. Okay, so then that probability is of our random sample. So we're doing the area to the right. We want to find the area to the left. So the area to the left is 0.6772. To find the area to the right, we would subtract them. 1 minus 0.6772, 0.3228. So what's the probability that if you randomly select 20 adult men, what's the probability that their mean will be greater than 175? So it's not super high. It's less than half of 0.32. Okay, so these types of calculations are used by engineers when designing ski lifts, elevators, escalators, and airplanes. So whenever we interpret results of the central limit theorem, if under a given assumption the probability of a particular observed event is exceptionally small, we conclude that assumption is probably not correct. So assume that the population of human body temperatures has a mean of 98.6, as is commonly believed. Also assume that the population standard deviates at 0.62 degrees. If the sample size is 106, randomly selected, find the probability of getting a mean of 98.2 degrees Fahrenheit and lower. So the probability that our sample mean, is less than 98.2. And we can write less than equal to or just less than. So since we're starting with a sample mean with a sample size of 106, we are going to find our z-score with sigma divided by square root of n. So this would be 98.2 minus 98.6 over 0.62 divided by square root of 106. Negative 6.64 is our z-score. If we think about that with our normal distribution, this is 98.6. Or if this was just our mean of 0, where would negative 6.64 be? This is one standard deviation, which is a majority. And then we have 2 standard deviations, which is about 98%. So where would negative 6 standard deviations be? It'd be like way down here, right? So what kind of probability would that be? Very, very low. If you look at our negative z-scores, negative 3.5 is as low as it goes, and it's 0.0001. So what that means is it's going to be 0.000001. So it's really, really a low probability. Be that far. So we can say this is a rare event. So this is probably not correct. So it's a rare event. Okay, let's go ahead and do example 5, the last one. Cans of regular Coke are labeled to indicate that they contain 12 ounces. Data set 19 in Appendix A lists measured amounts for sample of Coke cans. The corresponding sample statistic is that N equals 36 and our X bar is 12.19. Assume that Coke cans are filled with a mean of 12 ounces as labeled, with a standard deviation on 0.11 ounces. Find the probability that a sample of 36 cans will have a mean of 12.19 ounces or greater. So it's a probability that the mean is greater than 12.19. And we're looking at a sample size of 36. So our mean is 12, and we're looking at 12.19. And we're looking at greater than . So our Z is going to be 12.19 minus 12 over our standard deviation divided by square root of 36. Okay, so look at that Z-score. What do y'all think about that Z-score? If we have it, where would that Z-score be? That's like way over here, which this looks bad. So is this, these results suggest that the Coke cans are filled with an amount greater than 12 ounces? No, that's very rare. No. This is very rare, so it'll be a very low. Not likely to happen, ever. Okay, correction for a finite population. When sampling without replacement, the sample size is greater than 5% of the finite population N. Adjust the standard deviation of sample means by multiplying it by this square root, where N is our population size and little n is our sample size. For most of our samples, we use a sampling with replacement, so it doesn't exceed the 5%, so correction does not apply. Very rarely you'll use this. All right, so tomorrow we just have a short 6.5 page of notes. So tomorrow you'll get to do 6.5, not 6.6, and then work on your notes. I mean, your My Math Lab.